So here's a question for you. Is the world around you really there when you're not looking? Now, that sounds like something you'd ask in a late night dorm room, right? But it's a question that literally split the world of physics. It put the great Albert Einstein in one corner, fighting against a totally bizarre new reality. We're going to dive deep into that mystery and the spooky discovery that changed, well, everything.
Nobel laureate Alan Aspect really hits the nail on the head with this. He says we've basically been brainwashed since we were kids to just accept things. Think about gravity, an invisible force that just reaches across totally empty space. Newton himself, the guy who came up with it, thought the idea was absurd, but we just go, yep, makes sense. So what if the universe is hiding something even weirder? Something that completely shatters our basic ideas of cause and effect?
I mean, what if you could have two particles, separated by light years? I'm talking opposite ends of the galaxy, and they're linked. So perfectly linked that if you poke one, the other one instantly feels it. It sounds like something straight out of Star Trek, right? Pure science fiction. Well, this is the story of how a bunch of brilliant scientists proved it's not fiction at all. It's fact. And in the process, they had to pretty much tear up the rulebook for reality itself. All right, so let's rewind. Our story really gets going in the early 20th century. This was a time when everybody thought physics was, pretty much figured out. The world of Isaac Newton was this beautiful, orderly, clockwork universe, but some serious cracks were starting to appear in that perfect facade. So the first little crack comes from Max Planck. He's wrestling with this really annoying problem, and the only way he can solve it is to suggest something kind of crazy. That energy isn't this smooth, continuous flow. He says it comes in these tiny, discrete packets he called quanta. Honestly, he thought it was just a mathematical trick to make the numbers work. But then, in 1905, a young patent clerk named Albert Einstein comes along and says, nope, this is real. He shows that light itself is made of these little packets, which we now call photons. And that just opened the floodgates. Because if waves like light can act like particles, this guy Louis de Broglie asks, hey, maybe particles like electrons can act like waves. Turns out, he was right. And just like that, physics was completely turned on its head. And this led to a massive, mind-bending headache for everyone called wave-particle duality. Just try to wrap your head around this. How can one thing, a single electron, for example, be a tiny, localized bullet in one instant and a spread-out, rippling wave the next? I mean, those are complete opposites. It's like saying something is both a single grain of sand and the entire beach at the same time. This wasn't some little weird quirk. It blew up the very idea of what an object even is. Okay, so this wave-particle thing raised a massive question. If an electron can be a wave, what exactly is waving? The answer was about to completely demolish the old-school, predictable clockwork universe that everyone knew and loved. The answer came from a physicist named Max Born, and man, it was a bombshell. He proposed that this wave isn't a physical thing waving through space. No, it's a wave of pure probability. Think of it like a weather forecast map that shows you the chance of rain. The wave function is just like that, but instead of rain, it's showing you the probability of finding a particle right here or over there. The highest part of the wave is just where the particle is most likely to be. And the implication of that is huge. At its most fundamental level, the universe isn't a predictable machine at all. It's a cosmic casino, and it's all governed by chance. And here's where it gets really, really weird. The implication is that before you measure it, a particle isn't in any single place. It's just a ghostly cloud of potential, of possibilities. But the moment you look at it, the moment you measure it, that cloud collapses and the particle suddenly snaps into one definite location. It's like the universe is forced to make a choice right then and there. In a very real sense, your observation brings that reality into being. Now, a lot of physicists at this point basically adopted a motto, shut up and calculate. I mean, the math worked perfectly, so who cares what it all means, right? But there was one person, the biggest name in physics, who just could not let it go. Albert Einstein. He absolutely, fundamentally refused to believe that the universe was built on random chance. And that's where his famous line comes from, God does not play dice. For Einstein, this randomness wasn't a feature of reality. It was a sign that the theory was broken. He was convinced that quantum mechanics was just incomplete. He believed that underneath all this apparent chaos, there had to be a deeper, hidden, more orderly reality, like the gears of a clock that we just hadn't found yet. So this set up one of the greatest debates in the history of science.
In one corner, you have Einstein and his idea of local realism. This is basically just common sense, right? It says two things. One, objects have definite properties, even when we're not looking. A ball is still a ball. Two, nothing can travel faster than light. Locality. Simple. In the other corner, you have Niels Bohr and the quantum crew. They argued for a contextual reality, which is the mind-bending idea that a particle's properties literally do not exist until you measure them. It was common sense versus quantum weirdness. So to try and prove that quantum mechanics was incomplete, maybe even a little bit silly, Einstein came up with a thought experiment to highlight its absolute weirdest prediction. He called it spooky action at a distance. We call it entanglement. The idea goes like this. You create two particles that are linked, like a pair of magic gloves. You send one to Mars and keep one on Earth. Quantum mechanics says the moment you look at your glove and see it's a left-handed one, you instantly know the one on Mars is right-handed. Instantly. To Einstein, this was just plain absurd. It seemed to break his own ultimate speed limit. Nothing can travel faster than light. And for decades, that's where things stood. It was a philosophical debate, not a scientific one. You couldn't run an experiment to see who was right. It was just Einstein's gut feeling against Bohr's bizarre new physics. But then, in the 1960s, a physicist came along who figured out how to take this argument out of the philosophy department and put it into the lab. He found a way to put reality itself on trial. That physicist's name was John Bell, and what he did was pure genius. He basically said, okay, if Einstein is right, if reality is local and objects have pre-existing properties, then there's a hard limit on how correlated these entangled particles can be. He did the math and came up with a number, a line in the sand. If the correlations in an experiment stay below this line, Einstein wins. But if the correlations go above Bell's limit, it would mean that spooky action is real and quantum mechanics is right. All of a sudden, this philosophical argument became a testable prediction. So, the stage was set. The gauntlet had been thrown down. We had a clear mathematical question. All we needed now was someone to build an experiment sensitive enough to actually measure it. And this is where the guy we met at the very beginning, Alain Aspect, steps into the story. So in 1982, Aspect and his team in Paris did it. They built the experiment. They started firing off pairs of entangled photons and measuring them. And they did something really clever. They changed the measurement settings at the last possible nanosecond, while the photons were already flying through the lab. This closed a huge loophole. The entire physics world was holding its breath. So, what was it going to be? Einstein's comfortable, common-sense reality, or the spooky, weird world of quantum mechanics? The results came in, and they were crystal clear. The experiment didn't just cross Bell's line in the sand, it smashed right through it. The correlations were way higher than Einstein's reality would allow. The conclusion was inescapable. Einstein was wrong. The universe is spooky, it's non-local. And this is just a stunning moment for science. Think about it. A deep, philosophical question about the very nature of existence was just answered. In a lab, with lasers and detectors. That spooky action at a distance that Einstein thought was a fatal flaw in the theory, turns out it's not a flaw at all. It's a fundamental feature of the way our universe is built. You can see just how mind-blowing this was from this quote by Aspect himself. He said he was schizophrenic about it. On the one hand, he was convinced by Einstein's powerful logic, but on the other, he knew quantum mechanics just worked. It was unbelievably successful. It goes to show you how deeply counterintuitive this whole thing is. The guy who ran the experiment that proved it had to be dragged kicking and screaming to the conclusion. So what does it actually mean to live in a non-local universe? Well, it means that this spooky, instantaneous connection is real. But, and this is a really big but, you can't use it to send a message faster than light. So Einstein's ultimate speed limit is safe. Why? It comes back to that built-in randomness. You can't control what outcome you're going to get when you measure your particle. It's like having two magic coins that are guaranteed to land on opposite faces. If you flip yours and get heads, you know your friends is tails. But you couldn't decide to send a heads signal. The outcome is random. So there's a connection, but no communication. And that really brings us back to what Alain Aspect said at the beginning. Every time there's a huge leap in physics, it introduces ideas that just seem bonkers at first. An invisible force called gravity reaching across the solar system, invisible electromagnetic fields filling all of space. Those ideas were just as bizarre in their day as non-locality seems to us now. It seems like the history of science is just a long story of our common sense trying to catch up with the way the universe actually works. We just have to accept it. Reality is a whole lot weirder than we're built to believe. And that's really the big takeaway here. This incredible experiment answered one huge question, settling the debate between Einstein and Bohr once and for all. But in doing so, it opened up a dozen more. If two things can be connected without anything traveling through the space between them, what does that say about space itself? Is it just an illusion? What does here and there even mean in a universe that's stitched together by these spooky, instantaneous threads? This is the wild, beautiful, and deeply strange reality that science has uncovered, and we are just getting started trying to figure it all out.